Hello everyone, happy to finally catch up with you in session 5 of the December Code Power 2 Bootcamp, Web 3 Developer Bootcamp. So today we're going to be talking about a subject that is rather non-technical, and I'll type it here. I don't have a proper presentation, but yes, this should work. You should be able to do the concepts. Classification of layer 2, blockchains. Let's integrate it like this. This is the theme of today's session. Classification of layer 2 blockchains. So hopefully yesterday you covered details about what a blockchain is. And by now you should know things like consensus mechanism. You should know things like gas price and gas fees. So I won't be getting into the details of that, but I'll be just focusing on what these are, why is it important that we understand how they're each classified. There's quite a number of them under different categories, and we'll be looking at them today. Okay, my name is Emmanuel. I think I shared the link to my credentials here. You can reach out to me, or you can follow me on X, you can follow me on Farcaster, you can follow me on GitHub. Yeah, let's have a chat. So maybe what I will do to make this session a little bit more interactive, I'm going to type session here. I don't know if my screen is visible. This is session 5, I believe. Hopefully the previous sessions have been quite edifying for everyone that has attended. Okay, so let me see what do I do. So you can enter your name if it's going to be your very first time joining the session. Let me share the link to the Rise Up pad in the chat so you could be able to put your name here, and anywhere we can plug into you. And I'm just trying to find a single word so that I don't keep repeating it here. Just put the name here. Yeah, everything else should be on my identity. Oh, let me just type handles here. So your name and your handles, whether it's X, whether it's okay, just to be a little bit more organized. Put this right below. So you enter your name and your handles. Yeah, so we can reach out to you and see how we can get in touch. Let's follow each other, let's support each other's work. Yeah, push us very far. Right, so that's me. If anyone wants to enter their information, just copy this, then maybe change the name and handles. So let's say this is number 1. Okay. Yeah, so that's it for that. Yeah, so today the subject we're looking at, like I said, is classification of L2 blockchains. So maybe to come to the definition of what an L2 blockchain is before I go into the details, I'm going to type it here. Layer 2 scaling solutions. So you might be wondering, I don't know if you actually looked at this, but yeah. So here it says there's secondary frameworks built on top of blockchains, like Ethereum or Bitcoin, to enhance transaction speed, increase throughputs, and reduce fees. So we're going to get back to this definition in detail after looking at something that actually emerged, a challenge or a hindrance to progress or efficiency that emerged when blockchains were being created. So most of these blockchains actually experience this. So there's a phenomenon called the blockchain trilemma. You might have heard about it, you might not have heard about it, but I'm going to explain it here. in a few terms, and you'll be able to understand it. Then it will drive us right into why L2s are necessary, and how they well positioned as a solution to these big problems, to these three problems. So it's a trilemma because it's a combination of, it's a trinity of problems. And I will write them. I explain them one by one. So the very first problem is scalability. The second is decentralization. The third was security, or the third is security, because they still pose themselves as a problem to the efficiency of blockchains. So usually, typically what happens is that if a blockchain solves two of these problems, the other remains still in existence, permanently in existence. It's as if solving one problem enhances the presence of another. And how does that even happen? So when you think about it, more like you might have already seen, I don't know if I can create a new tab here. Okay, just want to try and reduce this in size. Okay, so the blockchain trilemma, we've seen the issues. There are essentially three: scalability, decentralization, and security. So what scalability essentially is, when you think about it, a single blockchain could be running probably a few transactions a day. So for instance, let's say we had a hypothetical blockchain. That is ideal. Let me just give an example of Ethereum. So for instance, when you think about Ethereum as a chain, it runs a number of transactions a day. Let me look at the Explorer. I'll show you something that makes sense in this regard. So when you think about Ethereum, today it might have run about, let's say, maybe 3,000 transactions today. You see the point? So for these transactions to be executed fully, something has to happen. The network has to have capacity to accommodate 30,000 transactions on a particular day. But this is what happens with computing infrastructures. As people continue to adopt the technology, as people continue to adopt this specific technology, yes, there's an overload in the infrastructure, there's an overload in the compute power, there's an overload in the machines that are doing that specific task. So in the same regard, even Ethereum, it is decentralized, yes, it is it is a set of nodes distributed around the world. But the more people use the more people use Ethereum as a chain, what typically happens is the network is overloaded, and sometimes it could slow the efficiency, it could slow the network, it could make it more expensive. According to the way it was architected, the busier the network, the more expensive it becomes for people that are running transactions. A very specific characteristic event happened regarding this issue. I don't remember the year, but let me look at. Let me try to find the news. I don't know what words to type, but this was actually the origin of the entire idea of creating layer 2s. Yeah, so there was a collection. Okay. Let me ask my best. My best assistant. What is the NFT site that inspired into solutions? Hopefully, I find a meaningful answer. So there was a collection of, yes, it was in 2021. There was a collection of NFTs called CryptoPunks. You might have seen them. Some of you might not have seen them. So what typically happened is that so many people were minting these NFTs and it was overloading the network. The way it was architected originally, Ethereum at that time, it didn't have capacity to accommodate this amount of transactions in a single second, or in the time period in which these transactions are being delivered for verification. So it caused an issue, and there was actually a jam on the Ethereum network. So people were not able to transact. Those that had the capacity to transact, you had to provide a lot of money in terms of gas fees for the transactions to get through and get validated. So you can actually see what it says. It says the major NFT sites that inspired such an innovation of L2 scaling solutions occurred in 2021 when Ethereum-based NFT marketplaces like OpenSea, Ethereum, and CryptoPunks saw explosive growth leading to severe congestion and skyrocketing gas fees. So imagine if you wanted to just mint a single NFT. So an NFT, like we'll see in the future, is just a digital asset. So if you had to pay approximately 1,000% of what you would typically pay just to mint that NFT, I don't think it would be something that is sustainable if you are going to be probably doing it as a business or you are just exchanging these tokens. Even making a minting of just a single one becomes very expensive every time. So that's typically what happened and inspired the innovation of L2s. And coming to that, I was talking about scalability as an issue that most blockchains have faced, based on how they have been architected. So Ethereum as an L1, it did not have capacity to handle those transactions at the same time. And because it was already a protocol that was designed, they had to devise another mechanism for being able to accommodate ever-increasing amount of transactions. Because I can assure you, the number of transactions that were being executed during this period when there was a surge, I think has increased to this day in 2026. We might be accommodating this number of transactions in Ethereum as efficient as it is right now because of the capacity that Ethereum has to L2s. It wasn't possible in 2021 because they had not created a solution that was ingenious against this issue of scalability. So what scalability essentially is the capacity of running of a blockchain to accommodate an ever-increasing number of transactions. So even if today the transactions on Ethereum increase by about 20%, ideally it should be able to accommodate those transactions. So it has the capacity to accommodate as many transactions as possible. Maybe up to infinity, I cannot determine, until their compute power is overwhelming, which we cannot determine right now because of the possibility of L2s and how much people have adopted L2s. We'll look at examples of L2s. But now Ethereum can accommodate as many transactions as possible. So I was talking about this number of transactions increasing in terms of scalability. So where is the thing? Okay. So I talked about scalability. Now I want to talk about decentralization. So what decentralization simply means, generally, is a distribution of a certain entity. Could be anything. So we talked about decentralized governments, for instance, where power is distributed. It's not concentrated in by a single entity, maybe the state owning body at the very top. That would be probably the president or the prime minister for certain countries. So it's not just that one person that holds the absolute power over everything, but the power is distributed across a number of stakeholders. So it could be one person at the top, but instead of them making decisions for everyone else, get the point? So this would be absolute centralization. So there's one person at the top, but he makes decisions for everyone. That's what centralization would look like. But then decentralization, on the other hand, would look something like this. There's one person at the top, but they have delegates, perhaps, that then have a restricted amount of power to execute on certain things. They're more like proxies, but they do have the agency to determine certain decisions that are supposed to be made in certain instances. So that's what decentralization would look like in a hierarchy of centralization. So it's just a semblance of an environment that has distributed power, although there's still someone at the top. Decentralization in the context of Web3, in the context of blockchains, is power distributed to people at the same level. You get the point? So these would probably be nodes. These would actually be nodes. So a node is just a single computer in a blockchain network, or a peer. It's called also a peer. So these would probably be nodes. So it's decentralization. This is what absolute decentralization looks like, and this is the decentralization that is referred to when we're talking about decentralization in the context of blockchains. Operations that are governed by a network of nodes operating at the same level, with the same privileges, with the same rights, and they are governed by a consensus mechanism that is written in code. So that means all the rules that govern how these people interact with each other, all the rules that govern how those nodes, those computers interact with each other, are written in a source code that runs on that blockchain, which is called the consensus mechanism, which is called the blockchain core. So the blockchain core constitutes the consensus mechanism, the mechanism by which all these nodes agree on certain operations and certain decisions, as we will see later. So that's what decentralization essentially is. Now, in the context of the classification of L2 blockchains, decentralization as a problem is about the scale of decentralization. Like how much distributed is a network, or how much centralized is a network. So you could see this is probably four nodes, or typically 4 computers. And I'm going to show you these 4 computers can make a blockchain. So you see that? But it's a set of 4 computers, or 4 nodes. This could be the only validators, or the only operators on that blockchain. So that would be a blockchain of 4 operators. We can all agree that that is a very small number of validators, or a very small number of operators. And that is a problem. So the smaller the network, the riskier it is, in the sense of how consensus is achieved. But the wider the network, so this could scale up to thousands of computers. Like for instance, Ethereum has millions, there may not be millions, but at least over 10,000 validators. I don't know if there's any way I can find out how many validators Ethereum has. Up to about 1.2 million active validators. That's a very big number of validators, and they're all around the world. As you can see, they're distributed globally in over 80 countries. So what that simply means is that all these validators, before anything is accepted on Ethereum, the majority of them the majority of them have to agree to that particular change or to that particular state modification that a specific account wants to make on the blockchain state. So, for instance, if you're transferring funds from one account to another, 60% of those validators, ideally 60% of those validators, have to agree for that transaction to be accepted in the Ethereum blockchain. It's a very large number of validators. What that also means is that if someone wants to manipulate the data, or maybe they want to modify a certain account's balance, what they would have to do is to convince 60% of all those validators on the Ethereum network for them to be able to make a change like that. It is very, very impractical because how permissionless systems work, this is a little bit advanced, but I will talk about it. These validators don't even know each other. That is the point. Because for you to get accepted as a validator in a blockchain like Ethereum, all you need to do is set up your configure your network, configure your machine to be accepted as a validator on the Ethereum network. But not every other validator doesn't even know what doing this. And then the blockchain data will be synchronized on your machine. That is it. That's all that it requires for you to become a validator on this network. Of course, you have to make a stake, but that's something we'll talk about still later. What it simply means is that you join the network anonymously, and so that means every other validator that is serving the same role as you does not even know you. Now, the bigger the network, that makes it even much harder for any data manipulation attacks to happen. Because what typically happens is if someone suggests a change, consensus has to be achieved. All these nodes have to accept that change. So the smaller the number of validators, the easier it is to convince each other to modify the data. So for instance, if you are storing funds on this network, and it has only 5 validators, they might even know each other. So there's a possibility they could gain your account simply by coming to a consensus and agreeing to make certain changes to the network state, including wiping your balances or modifying certain state changes that are involved in applications you might have built on top of that network if it is smart contract capable. So, about decentralization, the issue was about scale. How big is the network? How small is the network? It is about scale because this scale is a problem. How big is the network or how small is the network? All of these have a way they impact the efficiency, the security, and the capacity of the blockchain to be reliable. So those are 2 things I've been talking about. The third is security. Now this is dependent on the other 2, especially decentralization. The security of a network is a function of the reliability of the network in terms of data integrity. So for instance, if we have made a transaction, if I make a transaction right now and I send funds to another person, blockchains are supposed to have immutable states. What that means is if I make a transaction right now, the data that has been recorded on that blockchain regarding that transaction cannot be changed. But this is dependent on the consensus achieved by the different validators in the blockchain. That means that the more they are, the more secure the network. And the less they are, the less secure the network. So I'll use an analogy. For instance, if you are getting into a football field and we had one checkpoint. If we had one checkpoint, and each and every one of us had to go through that very checkpoint, we would have to go through much slower. We have to go through much slower because one, it depends on how tight is the security. How many layers of security do I have to go through to get through into the field? And then to how many people are we? So, like I said, it's dependent on all the other two. In that kind of situation, that security checkpoint doesn't have capacity to accommodate probably 30,000 people coming in all at once. They can accommodate 10 people coming in at once. So you can see how scalability is actually, how security is actually dependent on scalability. Because the truth is, verification has to happen. There's no question about that. If a transaction is supposed to be accepted as a valid transaction, it has to be verified. There is no bargain around that, because that is what guarantees the security, that's what guarantees the authenticity, that's what guarantees the decentralization of this network. That a predefined amount of validators has to go through a process of verifying that this transaction is actually true before it is accepted. There's no question about that. So that's one step of security. But when this security mechanism is being executed, is it possible that this network can accommodate a surge in the number of transactions that have to go through that process? That is where scalability becomes an issue. So back to my analogy, if a checkpoint into a field, a football pitch, would handle 10 people but can't handle 30,000 people, then there's an issue of scalability. What happens if there are 40,000 people? Will the network break down? Will we all be able to get into the field? In the context of my analogy, will we all be able to get into the field in time? Get the point? So that is one thing. The second thing would be, how many layers of security do we have to go through before we can get through the field? At some checkpoints, you may have to be scanned through, I don't know how they call that thing. It's like a door frame, but it's a security checkpoint, a security instrument. So you have to go through it. So probably if you have to get through that, then you have to be checked by another person physically touching you and then verifying if there's anything that may have been missed. Then you have to go through another layer of security, probably 3 layers of security. So the harder the security process to verify a transaction, the slower the chain is well. If security has to be rather lighter but still reliable, it makes it even easier. Transactions will get verified much faster because they don't have to go through very rigorous checkpoints, rigorous process of verifying them before they can be accepted. We're going to look at how L2s enable this as a solution. So typically what happens is that when two solutions are resolved, one still remains prominent. So I'll give an example of how this is actually an issue. So the more decentralized the network is, let's say it was widely decentralized, just talk about tens of thousands of validators. For a transaction to be verified on a network of this scale, it would require that we only take a sample of this number of validators to be able to validate transactions in a short time. Otherwise, if we have to require maybe 60% of these validators distributed all around the world, transactions would be much, much slower. So the network is decentralized, which ideally means it is more secure. But according to the mechanism, in the context of Ethereum, it would require up to 60% of all these validators for these transactions to be verified. What that simply means is that all these validators in the network, rather a significant percentage of all these validators in the network, would have to verify every single transaction before it's actually accepted on the Ethereum chain. That would take a very long time, which compromises on the scalability of Ethereum in that context, in the sense that if we had one transaction, it might go through faster, but if we had 15,000 transactions, we would have to wait for each transaction to get through before another comes through. We're going to finish the 15,000 if we have to rely on all 60% of the validators for a transaction to be verified. So it makes scalability an issue. So if we handle scalability, which means For instance, if you had a smaller chain, a chain of about maybe 10 validators, it is small, yes, that means transactions can be verified much, much faster. It is likely to compromise on security because these 10 validators could come together and agree on how they could manipulate the data in the chain in favor of themselves against the users that are using these blockchains. You get the point? So you might have achieved scalability, yes, in the sense that you can handle more and more transactions because they go through faster. Centralization, not very much. Security also not very much if the chain is even small. So for an even more decentralized network, there are looks at that and how scalability can be an issue, but depending on the architecture though. So what if we made the security much, much tighter? We want for a chain to be more reliable. So for a single transaction to be validated, it has to go through a number of steps of verification before it can be accepted. It will still compromise on scalability because then the process is much slower because it is more rigorous and much, much more difficult for transactions to be accepted. Well, that's the blockchain trilemma. It's a set of three problems that are very elusive. Up to this point, so many chains are still struggling with them. But yes, the advent of layer 2s as a solution to enable mostly scaling has been very effective against solving this blockchain trilemma issue. And yeah, getting back to the definition that we had earlier. So it says that secondary frameworks are built on top of blockchains, the Ethereum or Bitcoin, mostly Ethereum and Bitcoin, to enhance transaction speed. We have seen. We haven't just looked at them in classification, but we're going to look at them. So they enhance transaction speed, increase throughput, which is essentially the same thing, and reduce fees. So like we looked at it earlier here, we said every transaction requires an amount of gas fees, but the way Ethereum is architected in most EVM chains, especially EVM chains, the more congested the network is, the more expensive it is for you to have a transaction verified on that chain. So in this case, if the blockchain doesn't have the capacity to accommodate an ever-increasing number of transactions, when that time comes that there is an overload, transactions then become expensive to be accepted on chain because the gas fees skyrocket in favor of the transactions that will accept to pay the extra gas fees for them to be verified. And that's the scenario that actually happened during this period when there was a surge in NFT minting. The market prices were really booming. So those that were able to pay the extra gas fees are the ones that had their NFTs minted. It was actually a business, really. It was a very lucrative industry back then. So that's what typically happens when the network gets congested. And it's actually one of the core reasons why L2s were devised as a mechanism against scalability as an issue regarding transaction verification. So scalability, we talked about it, but also to reduce the gas fees. I think it was talked about here. So I'm using this as an alternative for a paper presentation, but yes, you should be able to see that space. And yes, there's a number of them. You might even know most of them. So I'm going to look at one of the most prominent sets of L2s in the moment. And they are classified according to categories depending on how they deliver each of these, how they deliver the issue, how they solve the issue of scalability, how they are architected to solve that issue. Mostly that issue. And we're going to look at a number of them in detail. So the very first category are called rollups. The most prominent category is called rollups. So what is a rollup? Now, typically, a transaction is verified singularly. Of course, there's when a block is going to be created and added to the chain, it has to go through a process of validation for most of the other nodes. But even a single transaction goes through verification itself. So if I have a single transaction, probably I'm sending funds to someone else. Let me say ETH is the native currency for the Ethereum chain. So if I'm sending ETH to someone else, this transaction has to be mined and added to a block, but it has to go through a verification process itself, and then also along with other transactions that are going to be put in the block where it's actually going to be included. But then, maybe I could look at blockchain explorer. I think I could look at so we can look at this practically. So this is Etherscan. This is the blockchain explorer for Ethereum. Not just the only one, just the most prominent one. So you can see it has the capacity to run this number of transactions. At least on average today there's been this number. This transaction throughput. 3,247 transactions every second. Let's compare this to the transaction throughput of Visa. Where does it stand? Let me see. Visa has quite an impressive one. Okay. Peak capacity of 65,000 transactions per second. Wow, this is very impressive. It's a number of transactions that could enable everyone around the world to trade at the same time. Almost trade at the same time. And from the average we have here, it is much, much higher. And yet still Ethereum is efficient. So that simply means that up to this point they've been able to achieve the goal of scalability. Of course, Ethereum as a chain itself, its protocol has kept being upgraded and made more efficient for things like transaction throughput, data storage. The most recent upgrade mostly optimized data storage and other components of advanced features in the blockchain protocol. But maybe later we can look at that. So let me look at transactions. This is the latest block, latest transactions. So for instance, when you look at this transaction, we should practically demonstrate this. You can see the status reads success. But before its status reads success, there's a time when it's going to be mined, when it hasn't been accepted yet, and it hasn't been validated yet. So it has to go through the process of verification before it's accepted as a valid transaction. And that's when the person on the other end would receive funds. Because this was a transaction of sending 0.1 ETH, approximately $247, was sent about 15 seconds ago. And yeah, that was a simple transaction. But if we had a million transactions that are going to go through that process in a single second, then it's going to definitely impact the efficiency of the network. That's where L2s come in as a solution. So we're looking at rollups and how they technically differ from a layer 1. So rollups are a specific classification of L2s, which are frameworks or blockchain built on top of other blockchains, typically on Ethereum or Bitcoin. So there are two types of layups, rollups rather. The very first one is called optimistic rollups. And the other is validity rollups. Or it is typically known as ZK rollups. Let's use validity rollups, it's more appropriate. So there's a difference between these two in the way they actually verify transactions. Typically, at that core concept between how they verify transactions. So I'm going to wish I can find the depiction. I can show you the optimistic rollups. Something that could show us in picture what's happened between these two and differs them from each other. Okay, that's the ZK rollups. Maybe let's find optimistic rollups first and explain something about them. Put this in here. So we could use it as an explanation. Okay, I think maybe this will be very, very helpful. So typically what happens with a rollup, different from what happens with an L1, like we looked at it here, you'd have a single transaction verified independently. It goes through the process of verification on its own to the end, and then another to the end, and then another to the end, and then they are put in a block. Then this is what is mined. So you have a block, and you can see here it actually shows us the latest blocks. Inside here there's a set of transactions, and they've all been mined at different times. So you cannot look at all the transactions here. This is the block. It has 623 transactions and 121 contract interactions. Let's look at them and look at the time at which they were created and verified. You'll notice that it's typically not the same time for all these transactions. This is ideally what happens. A number of transactions are bundled together, kind of like rolling them into one transaction, and then that transaction is sent to the underlying blockchain or the L1 as commitments, typically as commitments. So a commitment is just an optimized smaller version of all the transactions that is sent on that blockchain along with a proof. Okay. Let me see. So they all wait 3 minutes ago. It's just that transaction creation is so fast. I want to see this in seconds. Okay, we could look at this. This reads 15.123. 15.123. So this actually depicts number of transactions that can be accepted at a time every single second. You can see up to this far, almost all these transactions have been accepted. And since this block has how many? So 623 transactions. They cannot be accommodated in a single second because we saw the throughput is approximately 3,000, over 3,000 transactions I think every second. Remember to say that. Remember seeing that just a few seconds ago. So that means this block, you can see this, So 623 transactions can definitely be accommodated within this throughput every single second. So you might find a block being created in exactly the same period, whether all the transactions being verified in the exact same second, because the throughput is just enough to accommodate them. Okay, so we have that. And, so what typically happens is a proof is sent to the layer 1 blockchain that is uniquely representative of those transactions. So I want to demonstrate something here. Let me do it. I'm looking for actually here it is. So every single transaction has metadata. So that is information regarding the transaction, and you can see each of these transactions has information about it. The address it came from, the address it went to, if it was funds they were sending, and the amount of gas fees that were involved in that transaction, the gas price at that time. So all that is information regarding that specific transaction. So we have this transaction. And, this transaction hash is generated from all this information. It's uniquely representative of this transaction. So every time you have this transaction hash, it will always bring you back to this transaction. Let me look at more details. So all this information is representative of this transaction. It might look similar to information of another transaction, but it's not the same. One, because this transaction comes from a specific address, so even if a specific address sent 3 transactions with exactly the same parameters, they would look different because there is something called a nonce. So a nonce is just a number that represents, you can see this, nonce this. This always changes and it's different for every single transaction. This number here. So it's what represents a specific transaction, and it's what it's one of the characters, one of the features of the transaction that differs it from every other transaction, and how also this transaction has is generated to always be different from every other transaction, no matter even if all this information is the same, because the nonce is not the same. The transaction hash cannot be the same for 2 transactions. So imagine if all that information is put here randomly. So I'm just typing a little more details. Just imagine all this information represents a specific transaction. The nonce, let me say maybe the address a transaction came from, maybe a function name that we hold, probably this one parameter. We'll look at these when we look at transaction smart contracts. Maybe this was the address we were seeing in funds to. Probably this was the gas price. All this information regarding this transaction, maybe this was a nonce for that transaction. When I click generate a hash, I just want to generate a hash and demonstrate something that we'll use to explain proofs and how transactions are combined together. So you can see this is a mesh string, this is the MD5 hash, and this is the SHA-256 hash. When you look at this number, it uniquely represents those characters as they are. If I change even a single character, all these hashes would look different. So let's try that. Let's just change this 3 to a 4. And let's keep track of this. So I'm going to put it somewhere in my notepad and check if it's actually the same information. I'm going to copy only one. So I'll be tracking the SHA-256 hash. So this is the hash. But I changed just one number. This was 3, and I changed it to 4. let's see what happens when I generate a hash again. And see it looks completely different. See that? That's the hash that I generated by just changing a single character. But if I reverted it and turned it back to a 3, what would happen? With everything else the same, with everything exactly the same, the hash would always be the same. So the hash, oh sorry, this is the previous one. You can tell that the hash is actually exactly the same. So hash generation is deterministic in the sense that if you give it exactly the same input, it will produce exactly the same output. But even change of a single character in the data input will generate a completely different hash all the time. So in that regard, I wanted to talk about the float proof. So there's always a proof that is generated regarding this set of transactions. Now that proof cannot be tampered with because it represents those transactions very, very specifically. If you change even a single transaction among those transactions, the proof would look different. It would make the proof invalid. So the proof is always generated by for rollups. I was talking about optimistic rollups here, generally rollups anyway. A band of transactions is put together, then they are combined into a single transaction. And commitments are just small representations of those transactions independently. Commitments are sent to the layer 1 blockchain, and the proof is also sent to the layer 1 blockchain. That verifies that these transactions actually exist on this other network, in the second blockchain, the L2 blockchain. So you can see how that reduces the amount of data that is stored on the layer 1 blockchain, first of all. And then 2, how it scales the layer 1 blockchain. So now the layer 1 blockchain, instead of having to verify each of these transactions independently, the transactions that are sent into the L2. So if a block had to have about this number of transactions, on Ethereum, these would have to be verified independently. But on an L2, they are bundled into a single transaction, which is then sent to the Ethereum network as a single transaction with a proof and commitments. So commitments are very small representations of each of these transactions. So the data of these transactions actually remains elsewhere. It is not delivered completely on the chain, completely on the Ethereum chain. That's for Ethereum or on Bitcoin, if we're talking about Bitcoin. So Bitcoin also has L2s and layer 2 solutions. So now that scales Ethereum in the sense that it's able to accommodate a number of transactions because, by the way, there is not just one L2. There's a number of L2s. So if you have about 7 L2s, maybe 4, they're doing the single job that Ethereum would have done as a single network. They're each doing independently and then just sending proofs to the L1, which is Ethereum. This makes it even more possible for Ethereum to handle transactions more efficiently. Because now we have alternatives for where we can handle our transactions from. And there's a number of chains that are at this level that are layer 2s. And we're going to look at them. So we're looking at optimistic rollups and validity rollups. So what's the difference between the two? So it is in how transactions are actually verified in these specific chains. So the difference between a validity proof, rather a validity rollup, and or a zero knowledge rollup, which is also called a validity rollup. The difference between that and an optimistic rollup is that the proofs are different for each. So optimistic rollups operate with proofs called float proofs, while validity rollups operate with proofs called Just a minute. Yeah. I want to see a specific distinction. I'll get back to that. These are called validity proofs. So the difference between these two is the security assumptions that they take actually. So optimistic rollups, just like the name suggests, optimistic. When transactions are going to be verified on the L1 blockchain, the assumption is these transactions are actually valid, or that this rollup, a specific batch of transactions, is valid until someone comes up to say otherwise. And you have to provide a fraud proof against the data that you're trying to contest, against that block of, or rather that rollup, that specific batch of transactions. You have to provide a proof that verifies that these transactions are not valid, or maybe there's a fraudulent transaction among those transactions that were sent into the L1. Okay, that's it. And then for validity rollups, the assumption is that the transactions are invalid, so you have to provide a proof that these transactions are actually true. And then the other difference is that this is rather more immediate compared to the fraud proof. So fraud proof depends on someone actually tracking a specific batch of transactions, then later on verifying if those transactions are actually false, or there's a fraudulent transaction among them. But then this, the validators have to verify that these transactions are actually true. You have to prove that they're actually true. So you have to validate the transactions through the proof. On the other hand, the fraud proof does it the other way around. You have to invalidate the transactions. And usually what happens, there's a period that is designated for specific fraud proofs to be generated. It is not indefinite that after maybe a year you can still invalidate a certain set of transactions. The period is typically about 7 days within which you can provide a fraud proof for a specific batch of transactions. So beyond that, those transactions are immutable. That means there's nothing you can do about them. This is a flaw in the design of optimistic rollups. But I don't think there has been any very serious case around this issue as of yet. So for validity rollups, you have to provide the proof that these transactions are actually true. So as the proof is getting started, we'll be able to do this. Okay, so we have NFTs. That's the major difference between optimistic rollups and validity rollups. And maybe to get into the examples, you might have probably seen some of these rollups somewhere. Most probably you have, if you've been in the ecosystem for a while. So I wanted to show you a list of optimistic rollups. Many of them are already built under this architecture of optimism. So optimism is also an L2 itself. It's an L2, but so many other L2s are built on top of its infrastructure. Yeah, I could find them here. So you'll see most of them here, and probably you can go interact with them, look at their official sites, and see what developments they're having, and yeah, get to interact with most of them. So that's the first set of L2s, or layer 2 solutions. They're typically called layer 2 scaling solutions because the typical problem they were designed to solve is scalability. So they are scaling solutions. They make the chains that they scale have more capacity to accommodate transactions. No matter how many ideally how many. They should be able to accommodate them through these L2s. They could be optimistic rollups, they could be validity rollups. So for all ZK rollups, so the reason why these are called ZK rollups is that there is no requirement of the L1 to actually know about the transactions that happen, to actually have every information about the transaction, but depend on the proof that has been provided that these transactions are actually valid. Because the transaction, rather the proof is tamper proof, first of all, and it is generated in a mechanism that does not allow for manipulation. So there are two types of proofs under ZK. Also, still, there are those called ZK snacks. I don't know if you should put these fragments. You can go look at this. I'll do it as an assignment, so we don't get delayed by it. I need the rise up. Okay, I'll share this in the rise up. Let me put it here. This should be something you can take a look at and get to know the difference between the two. We will also introduce you to one of a very specific validity rollup for Ethereum called Stacknet. This actually coined the technology of ZK stacks. A special kind of validity proof that also differs from the other kind of proof called the ZK snark. It's really about efficiency and how one is faster than the other, mostly. Let me put them here for now as reports, so you can look at them. So yeah, that's it for rollups. Unless there are any questions right now. If you have any questions, you can raise your hand and we should be able to clarify an issue which you may be having. Any questions? There are no questions. Okay, I'll go ahead. If I'm not moving faster, so fast, you can give me a thumbs up or raise your hand and let me know. I'm having a little bit of explaining, but so we've looked at one class of L2s. That's rollups. There are other kinds of L2s as well that serve very specific purposes, not specific purposes that are architected differently. But let me first look at this specific side. So in the Ethereum ecosystem, the L2s are under some kind of scrutiny in terms of how decentralized they are, in terms of how they have scaled to the level of absolute decentralization, like is expected of them by the layer one from which they scale, And you can see each of them here are assessed according to what stage they've achieved. You can always come here and evaluate the status at which they have achieved, the status they've achieved in terms of them achieving decentralization. Let me first click on Habitron 1 maybe. Then I'll explain the simple details under here. So they are evaluated against each of these 5 characters. First of all, sequencer failure. So what a sequencer is, I didn't talk about this, but so a sequencer is the mechanism by which transactions are bundled together on the side of the L2 before they are actually verified in the L1. So it's like it bundles all the transactions together. And here it says in the event that a sequencer fails, Users can force transactions to be included in the project's chain by sending them to the LLM. Maybe let me we have an architecture here. Okay. So in case of sequencer failure, all this is verification that is done. This is evaluation that is done by the Ethereum ecosystem itself, because these are all EVM compatible L2s actually. So in case the sequencer fails, someone should be able to send the transaction directly to the L1. So if an L2 is able to do this, it gets some points in this scale of classification. Or if it's not able to do this, it loses some points on that scale. Then state validation. So it says fraud proofs allow actors watching the chain to prove that the state is incorrect. So this is what I was talking about earlier. So if someone is watching the chain, you can prove that a specific state of the chain is incorrect, and then raise a proof against that. And it's interactive, requires multiple transactions over time to resolve. So regarding state validation, how possible is it that someone can actually raise a fraud proof and it's accepted? Then data availability. Much as all this information is not sent on chain, okay, it says all the data needed to prove the proof construction is published in Ethereum LLM. So data availability. Usually what happens is the data is stored off chain for most of these chains. It is stored in a network called a data availability layer. There's a number of data availability layers, and I'll show you some of these data availability layers, where some of these chains, instead of sending all the data onto Ethereum, they send a little bit of the data just for that data to represent that these transactions actually exist elsewhere. Then the rest of the transaction information is actually stored in the DA layer, or the data availability layer. The most prominent one, you might have seen it, Celestia, but I think the most recent one is layer. So what this simply does is that it captures the transaction information from the different transactions that have happened on the L2s and then stores it. But of course, the L2 has to configure itself with that chain. Now, maybe we may not even find what we're looking for here, but that is the point, is that it stores the rest of the information regarding these transactions and enables persistence of this data. So one of the issues that Ethereum has been facing these days, not just these days, but as it continued to grow big, is that there was a lot of information that was being stored on top of it. That it was becoming unnecessary. So in the recent upgrade, they made a mechanism where transaction information is stored on the Ethereum chain for only a specific period of time. This is the period of time in which data availability layers have to capture that information and take it off chain so that they can persist the transaction information. Then after that period, if no one has taken that data, it is removed from the Ethereum chain. But of course, there are commitments that still represent that information. Now, of course, Eigenlayer also expanded into many other things, but it's one of those applications that are built for holding data for different transactions on different chains that do not store all the information on chain. The other is Celestia. You can look it up. Trying to look for the official site. Maybe we can check this out. You can look it up as well. I'll share these links in the Rise pad. So at the bottom here, in session 4, is this session 4? So this is research you can do on your own, ZK-Stacks and ZK-Snarks, to understand the difference and why ZK-Stacks was actually invented after ZK-Snarks already existed. and how more efficient it is. So you can look at Celestia, the DL layer. Of course, they've since expanded into many other things. You can look at Celestia, you can look at Agent layer. Yep, that's it. Okay. So are there any questions into this? In a single second. Okay. So those are rollups, essentially. I didn't get into very much detail, but let me look at the other classification. So these are rollups. By the way, the only thing that makes rollups different from most of the other L2s is that they use the exact same processors mechanism. Ideally, the same exact processors mechanism as the L1 that they scale. So we have rollups, then we have side chains. Now these are for specific website chains. We have state channels. We have plasma chains. But these have since lost relevance in the ecosystem, but they were once a thing. So what are side chains? So now a side chain is simply an independent chain, an entirely different chain. But the only difference between it and rollups is that it has its own processes mechanism and operates very independently. This one operates independently. But it's connected to the main chain via a peg. So that's like a bridge. It's connected via a bridge. Let me see if I can find the proper definition here. But that's essentially what it is. So just so Ethereum sidechain is an independent blockchain running in parallel to Ethereum mainnet. It's connected via a two-way bridge. So it has its own validator set, has its own processors mechanism. So unlike rollups, you can see these are the examples of sidechains that we have. Polygon POS and Gnosis chain. They do not inherit Ethereum security. So the thing that I probably didn't talk about is that for these L2s, specifically the rollups, they inherit Ethereum security in the context that all the transactions that are going to be verified, rather than send a proof to the L1, are now under the same scrutiny, shrouded under the same security that depends on the decentralization scale of Ethereum itself. That means for anyone to make a change in that proof, for anyone to make a change on those sets of transactions, they would have to now convince all the Ethereum validators to make that change, which isn't very practical like we're looking at. Decentralization. And Ethereum is sufficiently scaled, by the way. I think it's one of the most decentralized and widely distributed chains, if I'm not mistaken. About 1.2 million validators is a number of validators quite far above most of the other chains. And considering that they're all distributed around the world, it makes it very hard for you to make any attack on that chain. because of the scale of decentralization it's achieved. So I've been saying a sidechain is independent and interacts with Ethereum through a peg. So this peg is usually a bridge or a mechanism of communication between the two chains. For instance, if you're transferring assets across the chains, or if you're transferring messages to all specific smart contracts on each of the chains, it is effected through this bridge. And bridges have now become a prominent component of the Web3 ecosystem. It is now no longer between side chains like it originally was, but also between chains of completely different architectures. Like now you can bridge tokens from Bitcoin to Ethereum, from Bitcoin to Flare, which are entirely completely different chains. They're not under the same ecosystem or built for the same infrastructure, but there's this kind of mechanism that allows them to interact with each other, even though they are architecturally different. So that's what side chains are in comparison to rollups, is that they're independent, they have their own security assumptions. That means they enable their own security in that end. So if you attack a specific side chain, you have not attacked Ethereum per se, only in the context of if there are any assets that have been transferred across, they are already compromised on that chain. Or if anything happens on a specific side chain, it does not exactly impact the main chain it represents. So in this case, if we are looking at Ethereum side chain. So in case something happens to the Gnosis chain, it does not compromise Ethereum per se. It might impact the network at very many different levels, but only impact Ethereum maybe on the amount of, only on the number of assets that may have been transferred on the other end, and maybe awaiting certain operations on the Gnosis chain before they can be sent back. Otherwise, it's just the assets, not the architecture of Ethereum itself. On the other hand, if Ethereum gets an issue, most L2s will definitely be impacted. Okay. So those are side chains. Now state channels, on the other hand, are off-chain transaction. Let me say infrastructures. So ideally, what would happen if we had a transaction that we wanted to finalize? Let me first reduce this, then explain the state channels now. If we had a transaction that we wanted to finalize, for instance, this transaction right now, if we wanted to finalize this transaction, it has to go through that specific process of verification right now, just at the instant when it has been initiated. Now, depending on the scale of transactions that come after it, the network state, the network efficiency could be impacted. So many other things could happen during that time that could probably slow down the amount, the verification speed of this network. But what a state channel, on the other hand, does is that if two people create a state channel, probably two people have a state channel. So it's like a ledger, an off-chain ledger, through which they can interact and send transactions to each other. So this person will send transactions to that person, then this to that person, then this to that person, and you can have other people join this ledger and become a part of it. But it's off-chain. But how it actually gets all these transactions on-chain is that after a specific period of time, it delivers all this information on-chain in a single transaction. So it's mostly like a rollup. The only difference is that this keeps all the information off-chain rather, but it does not stop operations from happening. So all these operations will happen. Then at the end of the day, the transactions are settled. It's only that final state that is transferred on chain. So for instance, if I sent someone $300 and they sent back $200, at the end of the day, this person has $100, and then I have $200. maybe this is just a hypothetical situation. So at the end of the day, this is the final state that will be transferred on chain to a state chain. So all operations happen off chain, and then the final state is transferred on chain after a certain period of time. So that's the difference. That's the difference between the state chain, side chain, and the rollups. So plasma chains, on the other hand, they work similarly close to rollups. Let me first show you something before I can actually get into plasma chains. I want to first show you examples of these specific chains we've been looking at. These specific L2s. So we've looked at why L2s were necessary, and we've looked at the classification that they take. We've looked at the assessment scale that they take from the Ethereum ecosystem. You can actually get into details of these. If you want to understand a specific chain, for instance, if I probably wanted to know something about Stacknet, for instance, I should be able to see all the information here. Its own classification, also Stacknet is right here. And you can see they're actually classified by the proof system. You should give me something like that. Okay, you can see, oh, actually, I could use this. I'm looking for optimistic. The optimism bridge, but I could use this. You can see Arbitrum is an optimistic rollup. Base is an optimistic rollup. Optimism mainnet. Lighter is a validity rollup. Stacknet is a validity rollup. Ink is an optimistic rollup. So they are classified, these are rollups. They are classified according to the proof system that they use. And there is just a staging that they've achieved based on the classification by the Ethereum ecosystem. So maybe let me look at Stacknet, for instance. I can say, what does it say here about it? So it's a ZK rollup, it's a universal rollup, a universal blockchain. Some are specific to certain things. You can see the gas tokens here. So gas tokens are the tokens used to pay for transactions to be executed in that chain. Yeah, we can see a number of things about it here. Its activity, and chain costs. Yeah, anything you'd love to find out about a certain chain, L2Bit is a very good place to start. A specific layer 2 level. I'll put the link in the rise up link here. So yeah, also the information about what things it has achieved over the period of its existence. So Stacknet launched a new prover. Now the prover is the mechanism that generates those specific proofs about certain transactions. So it launched a new prover in October, and you can see how far it has come as a chain if you're interested in that specific chain. Yeah, so this is it. A lot of the information about the chain is always connected here. You can even go to the repository of their core contracts and some of the protocols that they have. So usually this will lead to maybe their libraries by the ecosystem that actually built it. So Stacknet was built by Stackware, and you can see everything is right here. Not everything, but most of the core components you need probably to build something on top of Stacknet. Yeah, there's more information here, but you can find a lot about Stacknet, including the projects that have been built on top of it as well. Yeah, that's it about that. Oh, actually, let me show you something. I just saw a link to a bridge. The bridge. So what a bridge is a protocol that allows for assets to be transferred from one chain to another. And you can see this one is called Hasstack Gate. For one of the, let me see, one of the most popular AI tools that we have that breaks the bit script right there. So if you want to transfer tokens probably from elsewhere to Stacknet, you can use this bridge, or from Stacknet to elsewhere, you could use this bridge still. The internet is a little bit slow, but essentially that's the classification of tools. Okay, maybe to ask again, are there any questions or anything someone would love to add before I could continue? Any questions? Okay. So this is the bridge. All you have to do is connect your wallet and be able to interact with Stacknet. So it's a bridge. Here you can see Ethereum and Stacknet.